So Alex tricked me into doing this. You'll note I'm the only co-organizer who's also speaking.
No, it's Stuart.
Okay, fair enough. Good. All right. Who's not here? But the idea was partly that Alex and Greg Howes and Elliot Quattard and a few others and I have been working for some time on using gyrokinetics tools from the fusion community to study problems outside the fusion program. And so we thought, Greg can't be here this week, he'll be here next week, but many of you will not be here at the same time. So really part of what I'm doing here is presenting some of what Greg has been presenting. And I've included some pedagogical discussions, so it's perfectly fine to interrupt and we talk about things, or we can go quickly and just get to the end where there's some results. Okay, so this little guy doesn't come through very well. At our universities we have mascots, and that's a turtle, which is the Maryland mascot before BP got a hold of him.
No, their mascot is a pelican.
Yeah, that's New Orleans, right, yeah. Or Louisiana. Okay, so several of you are up there on the board, and I guess Ryuska's coming later as well, yeah. The breakdown of work here, one thing it's worth noting, partway through this project we were using GS2, which is a tokamak and stellarator code, and it became clear that the code was too unwieldy to rapidly develop ideas. So we removed about 40% of the code, which was related to magnetic shear, to toroidal geometry, and therefore to twisted field line coordinates and all those things. And that made the code extraordinarily easy to try out new ideas in. And that code itself, AstroGK or AstroGeek, has proven to be very useful as a laboratory for testing these ideas. And I think over the next month, most of the results that people are going to be showing here at this meeting from the set of codes I work on are all from AstroGeek, because this code lets you do all sorts of good physics. And it's available online. And currently, Greg Howes at the top, Tomo and Ryuska at the bottom are the people in charge of that code. Okay, so here's an outline of the talk. Very brief discussion of what kinds of turbulence might be out there that we could address with and without gyrokinetics. Then talk about the theoretical understanding, motivating why we need to do simulations or what we might need to be able to learn from simulations. Then talk about the techniques of setting up the calculations and carrying them out, showing you a couple of results, and then that's about it. So, turbulence on Earth. Yeah, I've been watching the other speakers, and the colors are fairly faint in this room, so I tried to fix that, but it didn't help. Something about that projector. So anyway, there's lots of turbulence on Earth. I want to focus on simulations of turbulence, and maybe someday we'll have turbulence in something like that. That's the eater.
Maybe someday we won't.
There's plenty of turbulence now, but it's not the kind we can study. But this talk is more about turbulence in space and in astrophysical situations. And there are lots of different situations where turbulence plays an important role, from the largest systems such as galaxy clusters and the intergalactic gas, accretion disks, the interstellar medium, molecular clouds, convective stellar interiors, and the solar corona and solar wind. And I think given this morning's talks, I'm going to focus on solar wind applications. That's a trace picture of heating at the sun's surface. Turbulence is important. See, this picture didn't come through at all. That's too bad. This is my magnetosphere picture. Turbulence is important because of the dynamics. Turbulence governs frequently the transport of mass, momentum, and energy in lots of different systems. And we can look at the fluctuation spectra and get an idea if we were getting a good understanding of the dynamical systems going on in using a turbulence simulation compared to observations. But frequently in the astrophysical setting, the thermodynamics are more important than the dynamics. So in the example of a black hole, matter is spiraling into the black hole, and that's occurring through lots of processes. Among them, the magnetorotational instability, which is giving rise to the instabilities and the turbulence. That's the dominant mechanism. The turbulence in such a system will cascade to small scales, where kinetic mechanisms will damp that and lead to plasma heating. So the radiation that's emitted from a system like this is a strong function of the plasma heating. And so to interpret the X-ray observations requires a good understanding of the kinetic plasma turbulence and the resulting plasma heating. So that's what I mean by the thermodynamics. It's the heating. And in particular, as was discussed this morning, often the question is not how much heating goes on, because all of that turbulent energy will show up finally as plasma heat, or will be maybe carried away by some sort of outflow. But the questions are things like how much of the energy is absorbed by the ions as opposed to the electrons, and T-perp, T-parallel, and other things that might be diagnosable, and signatures. So if we just think of the simple world of hydroturbulence, the standard picture is that we have a long wavelength where the energy is injected. I guess there's no pointer. Oh, the big wooden one. Good. So the dynamics are important here. The specific things that are going on where most of the energy is are the things that we care about for the detailed dynamical evolution in the short term of a system. Then there's an inertial range down to some dissipation scale where the energy is absorbed. And the inertial range is hopefully large enough, both in theory, observation, and simulation, to be such that you don't care exactly how things are being stirred or exactly how things are being dissipated. We want to understand the physics of the inertial range. So I'm going to go slowly because we're going to use analogies later. A typical thing we might want to understand is what is the power law exponent of the energy versus wave number if you were to measure, simulate, or try to predict these kinds of spectra. And it's a straightforward idea from 1941 that everyone in the room should know, that basically the energy transfer is occurring locally in wave number, and if we can assume or verify this, and also find a situation where the energy cascade rate, that's energy going from one K to another as a function of time, is constant in the inertial range, so we're not dealing with highly intermittent systems or other kinds of confusing obfuscatory problems, then we can just do dimensional analysis, and we can say that this energy cascade rate from one wave number to the next has dimensions of energy versus time. A typical energy at a typical scale would just be the difference in velocities around an eddy, so that v squared sub k, it should say, would be kind of characteristic of the stuff going around and around in an eddy, if there's a characteristic velocity. And the turnover time is just the size of the eddy divided by the velocity. And so we can take the time and the energy together with the rate, and if we assume that the energy is being injected in steady state, flowing through to small scales at steady state without intermittency problems, then we get something like epsilon goes like kv cubed, and that's a constant from which we get that the velocity at a wave number k should go like k to the minus 1/3. If you square that and get an energy density by dividing by k, then you get the usual result, which is that E of k is going to go like k to the minus 5/3, and that's the Kolmogorov spectrum. So we're going to do the same thing in the plasma systems. But once what's the point of this slide? There must be something coming. Oh, see, we got 5/3. Okay, so we want to do the same thing in plasma systems. So we'll start with magnetohydrodynamics, where the scales are long. We're not worried about two important kinds of kinetic effects in particular, which would be gyration. We're not worried in particular about wavelengths of turbulence or eddy sizes, which are comparable to the gyration of any of the main particle species. And we're also not worried about long mean free path effects. So looking at a magnetohydrodynamic system, there are some differences already, even if we ignore the kinetic effects. And the principal one is that the magnetic field at the larger scales than the one you're particularly interested in is going to establish a preferred direction. And this anisotropy between parallel and perpendicular directions becomes very important. Similarly, actually differently, we're going to focus, just because it's easier and more straightforward and more consequential when you get to looking at all the data, the Alfvén part of the MHD spectrum is the most interesting part to think about. We could look at the fast waves, the slow modes, or the Alfvén waves, and for reasons that I'm not going to go into, but we can talk about, we'll look at the Alfvén spectrum and consider Alfvénic turbulence. So we need to think about the system. In order to pursue a program like the Kolmogorov program, we need to identify the conserved quantity and then find an inertial range between which, or between the stirring and the damping. And the conserved quantities will be things like v squared plus b squared integrated over the whole domain. So we'll take an equation for the velocity, an equation for the magnetic field, and we'll manipulate those in various ways. And so first thing is that we get the familiar Alfvén wave. And the dispersion relation then is that omega goes like k parallel v Alfvén. So Alfvén waves are like the waves on a string. If we, as hopefully Alessandro will play for us sometime during this meeting, if you pluck the string, you all know he plays guitar, right? So if you pluck the string, this wave will propagate along the magnetic field. And the idea is that from the initial equations, we can find that the velocity perturbation is proportional to the magnetic field perturbation, which means that we're not going to be able to distinguish in the theory the spectra of v squared from b squared. They're going to look very similar, which is of course what we saw this morning from the observational results. From Ohm's law, we just have that E is v cross b, so we find that the electric field, of course, is proportional to the perpendicular flow. And so MHD turbulence is going to give us, as long as we're thinking only of the Alfvén waves, something where the electric and the magnetic fields are proportional to one another, and we won't be able to, we'll get some kind of spectrum, which in a moment we'll see is k to the minus 5/3. And so to get to that, we need three additional hypotheses outside of what was done by Kolmogorov for the fluid turbulence. The first is something that's known as the Kryshnin hypothesis, which is to say, let's say we had some domain and there's a magnetic field which is at the large scales getting tangled up. One thing that comes to the fore in these discussions, even before we get to gyrokinetics, is separating the background field from the perturbed field and thinking about whether there's a mean field in the problem or not. And the Kryshnin hypothesis is basically that if we take a small domain inside the larger one so that this scale is characteristic of scales in the inertial range, then the component of the background, the component of the magnetic field, whether it has a mean component or not in the large domain, will have a mean component in the small region where we're interested in those fluctuations, and it will act as a mean field for these small scale fluctuations. This will support the idea that we can treat our turbulent magnetohydrodynamic system as a collection, again, we're focusing only on the Alfvén waves, as a collection of Alfvén waves on a mean field, so that when we're looking in the inertial range, we're thinking of a small patch of a larger turbulent plasma, and the mean field is simply a larger field which might be quite tangled, the component of a larger field which might be quite tangled. So this is data from Stewart, Bale, and the idea here is there's three components of the magnetic field versus time from cluster measurements, and the mean field is well away from zero, and the fluctuations are small compared to the mean field. So as the spacecraft flies through, there is, on average, some background magnetic field with small scale fluctuations on it. And that's going to be important for us. The second is started out in 1995, as far as I know, as a as an idea from theory and was later confirmed in experiments, observations, and simulations. And that is that the cascade itself is anisotropic in space, so that this background magnetic field, or the mean field on the scale larger than the one that I'm interested in, establishes a difference in space, and that the spectra of the energy fluctuations, v squared plus b squared, will be different depending on where we're looking, parallel or perpendicular to the magnetic field. So the basic idea is not just that if the magnetic field were up and we had some eddy, that it's going to tend to get squished. It's going to tend to cascade faster and get to small scales perpendicular to the magnetic field faster than it gets cascaded to small scales along the magnetic field. It's that this process is scale dependent. And so the scale dependence comes really from critical balance. This is also from the 95 Goldreich-Sridhar. And the idea here is that there's two time scales potentially in this turbulent alphanic MHD plasma. There's the linear time scale, which describes the rate at which these wave packets are moving along the magnetic field, these fluctuations. And there's a nonlinear cascade scale, which is basically proportional to the perturbed electric field, or perpendicular velocity, which is the rate at which, as two alphanic perturbations travel along the magnetic field and pass by one another, they distort. One distorts the other. And the typical time at which these distortions proceed is K perp V perp. It's a shearing in the perpendicular direction. And the idea from Goldreich and Sridhar was that the linear time scale, the time that it takes two eddies, two wave packets to pass through one another, is going to be comparable to the nonlinear cascade time, which is really to say that things will evolve in such a way that well, there's too many ways to say it, which will lead to a long conversation, so I'm going to leave it at this. And if we can simply say that we're interested in the system where the linear frequencies are comparable to the nonlinear eddy turnover frequency, then we get an interesting set of predictions. We find that we expect to see in the limit of strong turbulence that the parallel wave number, which is on the, well, this is a plot of power in a spectrum from simulations. This is K perp, 1 over K perp, and this is 1 over K parallel. And this line represents K parallel should be going like K perp to the 2/3, which is to say that there's this scale-dependent anisotropy. As you go to smaller, as you go to larger K, the disparity between K parallel and K perp gets larger itself because K parallel is not growing as fast as K perp. Okay, so we put all this together, and the dimensional analysis now, thinking of the perpendicular direction, the anisotropy gives us a nonlinear transfer time, K perp V perp. The energy cascade rate of K perp V perp cubed constant again gives us V goes like K to the minus 1/3, which of course gives us K to the minus 5/3 again for the energy spectrum. And that's V squared plus B squared. It's a function of K. Critical balance tells us that from this time and setting that time equal to the inverse, well, setting these frequencies equal to each other gives us that K parallel is going like K perp to the 2/3. So this is the scale-dependent anisotropy. And both of these things have been seen in numerical simulations and in observations, that as we look at smaller and smaller scales, the structures are more and more like spaghetti. Very long eddies along the magnetic field with sharper structure perpendicular to the magnetic field. These are the conditions under which alphanic turbulence seems to evolve. And what I think was first noticed by Elliott Quadert was that these are very favorable for giving rise to a gyrokinetic description of the turbulence when you get to scales such that the perpendicular wave numbers are comparable to 1 over the gyro radius. So we'll get to that scale in a moment. But the spectrum of MHD turbulence then looks extremely similar. The questions arise, what is this dissipation wave number? and what physics goes into setting this scale? Well, we're going to have to look at the kinetic problem a little bit to get a handle on that. And before we get to the dissipation wave number, which is going to be somewhere over here, we may pass through a point where now we have to keep track in our minds of the anisotropian wave number. So on this scale, I have K perp, and so there's some large scale stirring going on at long wavelengths. And if we assert that we're in the strong turbulence limit, we're going along here at every K perp. In this spectrum, there's a dominant K parallel. From the K parallel goes like K perp to the 2/3, so that we can also define that the typical turbulence eddies at this scale are also going to have some typical scale along the magnetic field. And I've drawn the line here when those eddies' parallel wavelength is comparable to the mean free path in the plasma. And so to the left of this line, we may have collisional kinds of development of real magnetohydrodynamic perturbations. And to the right, we're going into a collisionless regime. And in the collisionless regime, the perturbations along the magnetic field, the wavelengths of those perturbations along the magnetic field are now getting shorter than the mean free path. And so it seems that all sorts of things could go wrong with our description, and we have to be very careful. And so Alex has a long paper from a couple of years ago which talks about the fate of the various kinds of perturbations, not just Alfvén waves, but slow modes and so forth, as you go through this transition from a real magnetohydrodynamic description to needing a kinetic description. And the basic story is, we're going to break it into two parts. The first part is, what happens to the Alfvén wave cascade when we get to the scale such that K parallel lambda mean free path is greater than 1? And in Alex's paper in some detail, the answer comes back that the Alfvén wave cascade doesn't care. Continues undamped right down at least until we get to the ion Larmor radius, and we'll worry about that in a moment. So there's no real signature in the Alfvénic cascade, as you would expect, because there's no real damping or Landau kinds of physics going on with the Alfvén waves as you go through this point in the spectrum. And so, yeah.
Like when you go to this short wavelength regime, there is this wave becomes kinetic Alfvén wave, then there is a E parallel. And
yeah, but that's not yet. I've broken the problem into here. I'm saying that conditions could be such that first we will go to the long mean free path along the magnetic field, and that can happen in general at a different K parallel that corresponds to a given K perp, where we'll hit the gyro radius in a moment. So it's a function of collisionality versus B and beta and those other things. So it's not universal what I'm saying. The ordering
is still small.
So I'm assuming here that we're at such a weakly collisional plasma that we can get to, as we cascade along in parallel and perpendicular wave numbers, each at their own rate, that we'll first come in this picture to the transition where along the magnetic field lines things become collisionless, or the wavelengths are shorter than the mean free path along the field before we get to the gyro radius. And you're right, that line could be to the left, could be to the right, could be all over places. I'm just drawing one particular scenario.
What plasma pressure you're talking, like a beta? Is this what kind of plasma?
Beta doesn't really, this is more collisionality.
No, but I mean in general, like you don't talk about fast wave, like magnetosonic.
No, I'm focusing on the Alfvén waves. And that's really a decision. It's a decision which there are a set of systems which I'll talk about. I think I have a slide which describes 3 or 4 different systems where the Alfvén wave is what we think is the dominant thing going on. Typically, the fast wave is going to have some damping, shocking, various kinds of mechanisms where it will get dissipated quickly. The slow modes may be tumbled along, cascaded by the Alfvén waves, but the slow modes don't affect the Alfvén waves. And basically, the density spectra that we get, we think, are the density fluctuations which are being cascaded by the Alfvén waves, but they're not there's no density perturbation in an Alfvén wave. So those are slow modes being cascaded by Alfvén waves. And so what I'm talking about here is I'm ignoring the fast wave and I'm looking at the Alfvénic component. But it's a choice. So, so we go right through the wave numbers where the parallel dynamics becomes collisionless, and we don't care. The answers may begin to change, and I've chosen plasma such that by the time we get to the gyroradii scales in the perpendicular wave number, which I'm going to talk about next, we're already in the collisionless limit along the magnetic field, because that's going to be the most interesting case. And so if we zoom in some schematic fashion, and we could look at, here's a field line, and so now what do we have? We have that the particles are just mainly gyrating around this magnetic field line, and if we're so lucky with the values of beta and the nature of the stirring, then we'll find that the frequency of gyration of these particles is really quite fast compared to the rate of change of the magnetic fields or the eddy turnover time or anything else going on in the plasma. And that's going to be the case where we'll be able to use gyrokinetics. That's certainly not always the case, and the latter talks this morning talked about instabilities arising at the gyroradius scale from anisotropies in velocity space, which are different than the anisotropies in space associated with the fluctuations. I'm focusing on the case where those velocity space anisotropies are not present. And so the system then is going to carry on, and we'll get to the inverse gyroradius, K perp rho of order 1. And now we're going to ask what goes on there. So our Alfvén waves have cascaded along, and the question next is what happens to the Alfvén wave cascade when we get to K perp rho of order 1? And the notion is, this has been written out in several papers now, is that the Alfvén wave cascade transitions mainly, primarily, or wholly to a kinetic Alfvén wave cascade. And there's some very interesting questions about how much energy of the Alfvén wave cascade goes on into the kinetic Alfvén wave cascade, how much of the energy goes into other processes. I'm going to set that aside for a moment and just say that generally the underlying waves certainly transition from Alfvén to kinetic Alfvén waves, and that's going to have its own signatures. To get at some of the detailed questions, such as how much of the energy ends up in the kinetic Alfvén wave cascade as opposed to an entropy cascade in the ions, which we'll hear more about this afternoon, we need to do numerical simulations because the theoretical foundations aren't quite strong enough yet to tell us exactly what happens when we have that many degrees of freedom. So that's where we step in with numerical simulations. Let's look at the nature of the kinetic Alfvén wave so that we can decide what kind of simulations we need and what can we get away with under what circumstances. Well, now the wavelength of the wave, this is the electric field, let's say, associated with the kinetic Alfvén wave, is sufficiently short that the ions, I'm taking the limit now where K perp rho is bigger than 1 to make life easier. So the ions, this is some weird space where ions move in the direction of the electric field. It's just a schematic. So the ion gyroradius is now large compared to the wavelength of the kinetic Alfvén wave. And basically, the ions are averaging over, they're hitting the phase of the wave, they're hitting the amplitude of the wave at random phases because the waves are moving along and the ion gyroradius is large. So the ions decouple entirely from the wave, and we get no flow from the ions. Instead, the turbulence is basically supported by the electron motion alone. And so the perpendicular flows are going to be associated with the electron flows. And that will have implications. Let's work through those very quickly and simply. Ohm's law is again E is V cross B. But now the U perp is the electron flows. So this part of the derivation, you can think it looks very similar to EMHD, electron magnetohydrodynamics. But we don't have to actually use that label because that has some additional constraints built into it. I'm simply saying that at these scales, the electric field is going to be proportional to the electron flow. And when we look at Ampere's law, we're going to find that the electron current, J perp, is looking like K perp, B perp because of the curl. And so we've got ourselves a little bit different situation. Now E is going to be proportional to K times B. And that's why we're going to see the electric and magnetic fields diverge in a moment when we look at spectra. So for kinetic Alfvén wave turbulence, we expect E to go like KB. And now we'll be able to tell the difference between a velocity spectrum shape and a magnetic field spectrum shape because the K structure is different. So we expect differences to arise. Well, what are the waves themselves doing? This is a plot of the frequency of the wave versus the wave number of the wave in the perpendicular direction. And this is K perp rho of 1. And this is some hot plasma dispersion relation. And for fun, we put the AstroGeek simulation. This is just linear theory, but so it basically has to work. But the AstroGeek simulation results to show you later when we do nonlinear simulations that we have the right component waves. And the idea is that in the long wavelength limit compared to the gyro radius, we have Alfvén waves so that omega over K parallel V Alfvén is unity. And when we get to short wavelengths, or high K, omega goes like K parallel, K perp. And so it becomes a more dispersive, we get a dispersive wave. And that's what the frequency is doing. And that's going to play into our argument of what is in critical balance, because we needed to balance a linear time with a nonlinear time. As Andre noted, there's also damping that comes in when we start to make the transition from Alfvén waves to kinetic Alfvén waves. And this picture is at some particular beta, which I don't recall at the moment. But this is now the damping rate of the wave compared to K parallel V Alfvén. And so unity is way up here. So this is the linear frequency. And the damping rate is extraordinarily weak for small wave number. And as you approach K rho of 1 for this value of beta, probably beta of 1, but I don't really know off the top of my head. The damping is now a few percent, and as you get to K perp rho of 10, the damping can be quite strong, meaning that there's hardly any, the wave barely goes through a couple of periods before it's damped out and dumped its energy into the particles, and in this case, I'm guessing, I don't have the parameters in front of me, that it's damping on the ions. So, but the key is, now we have something new. We have that there's actual damping of the waves, and we have this frequency change. And so the kind of theory that is going to predict the observations that Stuart showed this morning is a theory that's going to have to kind of assume that we roughly understand what happens when the frequency changes as a function of wave number to a Goldreich-Sridhar type argument, and when the damping becomes of order of the linear frequency. And the reason we need simulations is to actually see what does happen given the equations that we're looking at, and then we'll go back and try to figure out how to compare that with the observations. So now focusing only on the magnetic energy, so this is now delta B squared as a function of K. We have the K to the minus 5/3 region. When we get to K rho of 1, because it looks like I dropped a slide or it's going to be out of order, but as was noted this morning, the magnetic field spectrum goes to K to the minus 7/3, and the electric field spectrum, if we were to plot it on here, goes to K perp to the minus 1/3, and the difference is just a factor of K squared, which is the same K that was between the E and the B. Yeah. Okay, we're nearly done. So on this side, we've got the fact that the waves are speeding up and that there's dissipation, bona fide dissipation. So there's dispersion and dissipation, and the various kinds of things that you can observe at high wave number have to do with the actual plasma parameters, namely beta and the collision frequency, and some measure of the stirring compared to the cyclotron frequency. So at the end of the day, the way in which this energy is either cascading on further and getting perhaps all the way to the electrons and thereby ending up wholly in the electrons, whether some of this energy, this is the magnetic energy associated with the kinetic alphane wave cascade, whether in fact there's a drop here associated with the launching of an entropy cascade in the ions, and the fact that this may turn into an exponential decay instead of a power law if the damping is strong enough. These are all things that we can look at with simulations. At any rate, the heating is governed by these kinetic phenomena, and so we can't get away with too simple of a model. All right, so what's our model? If we look at the interstellar medium, these are typical range of actually, this morning when I was looking at the slide, I guessed that this is the interstellar medium, so if any of you obviously see that's wrong, be sure and tell me. But when I made the slide originally, this is certainly a typical plasma in some astrophysical setting. There's a wide range of scales between the gyroradii and a typical wavelength that we're interested in, or stirring scale. And there's a huge range in frequencies. There's the very high frequency plasma frequency, there's cyclotron frequencies, and then there's a typical kind of alphane time of 10 seconds. So we have a good separation of space and time scales. If we wanted to just attack that with a straight up particle code or something like that, then we would need to resolve the Debye length. If we're looking at the gyroradius scale, then our box is going to be some number of gyroradii, and we would grid up all these lambda Debyes, give us 10 to the 12 points. We would also need to grid velocity space. That's a low estimate of what you could get by with in terms of velocity space. We'd also have a Courant-Friedrich-Levy condition, which would tell us that our time steps can't be too large. And when we take the product of the number of time steps and the amount of resolution that we would need, we get something like 10 to the 23 for number of mesh points times the number of steps, or particles times steps. And that's a big number. The state of the art is something more like 10 to the 16. That is 50 billion mesh points or 50 billion particles run for 1 million time steps. That's about as big as anyone I've ever seen do. And so we're off by 7 orders of magnitude. So this is yet another problem that we're familiar with from the fusion world that we can't do straight up pure direct kinetic simulation. So that's why we restrict our attention to that set of plasmas which have all the characteristics I've said and are gyrokinetic. And that's not all plasmas. Troy can dial up plasmas in LAPD which do not have a strong separation between the alphane frequency or alphane time and the ion gyroradii, the ion gyro period. And it's questionable, although we had a paper that looked into this, it's questionable at that point whether you have a good separation of timescales that you need to do a reliable, decent job with gyrokinetics. But there are other plasmas where the separation of timescales between the gyro frequencies and the scales, the time phenomena of interest are wide, and that's where we certainly can do gyrokinetics.
What happens to electrons in parallel direction?
In the code, they're moving along at 40 or 60 times the ions in the parallel direction, so that's still expensive.
Kind of adiabatic or not?
Fully kinetic.
Fully kinetic? But
Fully kinetic. Because we want to resolve, I'm going to show you results in a moment, where we resolve everything from larger than the gyroradius to the electron gyroradius. And so we have ion electron damping, electron Landau damping, all these things all at once in one calculation. So in the tokamak, we're looking at gradient-driven drift wave turbulence in a complicated, nasty geometry, and everybody cares because of oil spills and things like that, because we're trying to get away from that world. So this is hard for its set of reasons. Looking at space problems, it's really quite different. There's no background gradients that we're worried about. And so this is the difference between using a code like GS2 and AstroGeek. But nevertheless, the underlying technology and the understanding and the development of the algorithms carries through, and we can use the same techniques that we studied in this community to study ion temperature gradient, electron temperature gradient turbulence in fusion plasmas, and use those to work on this space stuff. Looking at the solar wind in particular, for the gyrokinetic description to be appropriate, in addition to the creation hypothesis and the other things that I outlined, we need 4 additional things to hold. We need that the gyroradius, this is basically k parallel rho, should be small. We need the gyroradius compared to the parallel wavelength to be small. We need the amplitudes of the fluctuations to not be large. This means that we can't study mirror modes which go to large amplitude because delta B over B becomes of order 1. It's not an appropriate problem for gyrokinetics. We need the anisotropy, which was really built into the discussion by the Goldreich-Sridhar problem. But if we were to run kinetic Alfvén wave turbulence with a gyrokinetic code and find that the parallel spectrum, the fluctuation along the magnetic field began to cascade more rapidly, or slowly, more rapidly, then we would get into trouble potentially. So we have to watch that the anisotropy continues, and we want low frequency. So in the solar wind, all of these are small numbers, and life is good, and we can do gyrokinetics, at least some of the time. So let's look at Stewart's data. We saw it this morning. In the inertial region, the velocity and magnetic field spectra are indiscernible, at least up to a constant. And as we said before, the spectra both go like k perp to the minus 5/3. And this is a simulation result from AstroGeek, which plausibly, at least it's consistent, that when we simulate a box that in the perpendicular direction, the gridding is such that we're not worried about k perp rho bigger than 1. Our boxes, could figure it out, several hundred gyroradii wide in the perpendicular directions and very long along the field line. We get that these guys are looking like k to the minus 5/3. More interesting is the region where the electric field shallows out, magnetic field gets steeper, and by the arguments that we were talking about before, just scaling dimensional arguments and wave arguments, we're going to expect that the magnetic field goes like k to the minus 7/3 and the electric field goes like k to the 1/3. And here are gyrokinetic simulations from the 2008 PRL, which was of limited size. But now we're keeping up to k perp rho I of around 8, and trying to look at this, trying to hope to see some divergence between the magnetic field fluctuations and the electric, and we do begin to see some. The new thing, here comes the new results. The new results have much higher resolution. So now we have a factor of, I think it's 50 in wave number, so we're stirring at scales that are large compared to gyroradius, and we're going all the way up to scales comparable to the electron gyroradius. And we got a real nice picture now of the electric field shallowing and the magnetic field going to something between k to the minus 7/3 and k to the minus 2.8, something like that. It's going to be steeper than the minus 7/3 because in this simulation we're actually observing dissipation happen in that zone, as well as the dispersion that comes from the pure kinetic Alfvén wave undamped argument. Okay, so Greg will be here next week and he'll tell you more about the results. And there's some detailed modeling that's gone on to try to understand what we expected based on those theories that I told you about. And the purple and the green dashes are actually predictions from a simple cascade model which builds in all those ideas. No, the solid line is the code.
No.
And these, what? I've got it the other way around? Fair enough. There's predictions and there's code.
They're the same.
They agree. Okay, so there's lots of things you can do now that you see you can run the code. You can look at how the field and density fluctuations vary as you vary the magnetic field and beta, the collision frequency relative to the Alfvén speed. We can begin to look at the disposition of the energy between ions, electrons, minor ions, and we can ask questions now, having learned these things. Is there any signature of the turbulent cascade that we've learned about from looking in outer space that we would see in fusion experiments, which would give skeptics a little more confidence that we're actually looking at the waves. We're modeling the actual waves that are happening in the experiments. So I'm told I'm done. So I'm done. Thanks. I have no idea why they have this sign here, but it's great. I know, but it's great. Please leave. Any questions? Discussion?
So, from your case spectra, it turns out that you drive the system at, what is it, k rho point something, 0.1, 0.3 or so.
Actually,
And
maybe
then-
it's...
and then the cascade seems to kick in pretty instantaneously.
Yeah, so how do we do that?
Yeah.
We use a... so I had a graduate student who recently defended, and she did what you might say would be the clean drive. She put in a monochromatic Alfvén wave by driving a current external to the plasma and getting a vector potential at the scale of the box, oscillating at the Alfvén speed. And what she observed was sort of disappointing. It took several Ks before the thing settled into a turbulent response. And moreover, because of selection rules of what can attach to what, there were lots of Ks which were just useless. A lot of the box was not being used. Instead, what we've done is we've got 3 to 5 modes, all low lying in the K space, maybe the 1-0s, the 1-1-1 and the 2-1-1 and the 1-2-1 and various things, with random phases. And each of the, instead of driving with monochromatic Alfvén waves, we're driving with the solution to a Langevin equation. So it looks like an Alfvén wave with some jitter. And we set the decorrelation time of the Langevin equation to be comparable to the frequency that we're driving the antenna at, which would be about what you'd expect from a critical balance argument. So we have 3 to 5 modes at the size of the box, each of which is being decorrelated on the same time scale that they have a frequency. And what you see is quite pleasing. It immediately settles into a nice spectrum, and you don't waste all those Ks. So that's what we do.
Wouldn't you still expect that some kind of beating or something is required? So a few steps, factors of 2 would be required?
It works pretty well. This is a heuristic idea, and we went into it. We've done, I don't know, 10 or 15 different simulations. These are expensive. We've done several at scale to see how the driving is affecting the solution. And we're not seeing any signatures of the driving in the solution, except if you go back to a monochromatic drive, there's lots of Ks that nothing's happening at the large side of the box.
For these parameters of simulations, beta is 1, right? You had somewhere.
I think it is, yeah.
So then you have a strong coupling to ion sound waves.
Yeah.
And
strong Landau damping.
Yes. And any shocks like nonlinear waves from ion sound, this modified Schrödinger type things.
This is a new set of simulations. I don't think we could see those things, but we haven't in any case. In the gyrokinetic ordering, the perturbations can only be so large. So even if everything's nonlinear, delta V over V thermal is always small, of order epsilon, which is infinitesimally small in these simulations.
But the shock will be
So it's not going to be shock.
density. Shock will be in density.
Delta N over N is also order epsilon.
But is there in these parameters there's this decay process Alfvén wave into
Right.
sound?
Right, so that means that we have to have a lot of resolution in velocity space, and we have to include some collisions. And the hard part of these calculations for the solar wind is that the actual collisionality that you would get from the parameters of the solar wind is so small that, in fact, that's the first place that we get into trouble with the whole ordering. We need the collisions to be at least strong enough to give us that the equilibrium distribution function is Maxwellian.
So the collisions is technical, right? It's like for simulations.
No, I'm talking about in the real world. Collisions for a gyrokinetic approximation, to be a valid way to proceed, the collisions need to be strong enough so that the background distribution function is Maxwellian. And that's a dodgy question in the solar wind.
There are debates about that.
Well, they're wrong, and I know you're wrong.
I'm one of those who thinks that that's not required.
Right.
That's obviously not required.
That's okay.
Antonsen and Lane derived the linearized
Linear.
gyrokinetic equation
Right.
for the general result. And
Right.
it's just not an essential assumption.
So if you want to talk about heating, then you need to have an equation that describes the evolution of the background temperature. And if the background distribution function can't be characterized as Maxwellian, then I don't know how to get that equation.
People who do RF heating have long studied the generation of non-Maxwellian tails, and as long as the particles become decorrelated and stochastic, it's still irreversible, even though the distribution function is not Maxwellian. So it's not an essential requirement.
And the other thing that goes wrong, and I do believe that we'll be talking about this for months, so let's just float the ideas clearly. The other thing that I would argue goes wrong is that if you don't have strong enough collisions, then you can't take the approach that, at least that we've taken, which is to ignore the next order terms that are like the parallel nonlinearity, and that give you particle trapping. There are people in the room who would argue that. And certainly we have enough collisions to avoid that phenomenon.
Collisions is one way to avoid the parallel nonlinearity, but it's not the only way, and again, you don't need it.
So the table is set for further discussion. Yeah.
Do you expect still power law scaling for spectral function, even for smaller scale, not smaller than electron gyro radius?
No, ultimately, even here, it's not clear that we don't expect in general power law scalings because there is damping, and if we were in the limit where the damping were strong, then we could get exponential. So in general, we're going to run the code and try to understand the regimes.
That kind of expected exponential damping is related to collisions, ultimately.
It's related to Landau damping. And if we go to scales smaller than an electron gyro radius, and we've not had any Landau damping yet, then I would expect a wave number from there along the lines of this free energy cascade, which we'll be talking about later this week or sometime, maybe at 5 when I give my next talk. Yeah.
All right, thanks, Gil.
Yep.